very interesting and cool topic mathematically, of course. So L'Hopital's rule. I didn't put the little circumflex. What's that little triangle thing in French? Is it? All right. Okay. Cool. I remember something from 5 years of French. The little 5 thing at the bottom is the cedilla. Yeah. All right. Accent aigu. Hold on. I think I got it. That's going out, right? Accent grave is going the other way.
I took French 2 years ago and I didn't even know that.
I mean, it's the little things. Little things. I mean, I get told repeatedly by French waiters to stop. Like, just stop.
It's my
So-
dad at school.
Like, I tried. Like, I did this for 5 years. Come on, I'm going to put my knowledge to, put it to work here. And they're like, no, enough out of you. Like, you suck. Like, we'll speak in English. Actually, one person said, s'il vous plaît, en anglais. And I was like, how do you say, let's meet in a parking lot in 15 minutes in French? Because you're a jerk. I was like trying to show off in front of my family, and you just shut me down royally. At a minimum, you're not getting a tip. So, anyway.
We don't take tips in Europe, so.
Yeah, I know. That was like, joke's on you, American. You know, so. So anyway, L'Hopital's rule only applies if you have this. I mean, there's a lot of fun stuff to see here, but it's talking about the indeterminate case. All right, so undefined, usually when we found a limit, undefined usually meant that we were looking at some kind of infinity or possibly a DNE. But when we had a 0 over 0 or infinity over infinity, that meant that we could come up with a limit, we just had to do some work. Unfortunately, at the time, some of that work involved us knowing some rules. If we didn't know the rules, we were out of luck. All right. This table here, did I say where I got it from? I'm pretty sure I just got it from Wikipedia. They keep telling me that I owe them money. You getting that? You getting that now? Like, you come here a lot. Give us $2.75. That's how much a cup of coffee costs. I'm like, actually, my cup of coffee costs, like, not $2.75. So, but still, I mean, that's not the point. The point is, I'm not paying you for something that's advertised as being free and open to everyone. Unless I can charge for my stuff. I don't know. Anyway, so these are different ways in which you can have an indeterminate form.
Charging for his website.
Charging for my website. I'll get 0 hits.
Just a cup of coffee.
All right.
Just
So 0 to the 0, that's one where you wouldn't necessarily think it follows the same form, but if we have something like x to the x power, then that technically falls under that category. It's an indeterminate form. All right, so it would still be under the umbrella topic of L'Hopital's rule. But generally those involve log differentiation, which is why we covered that topic already. All right, so anyway, how do you apply L'Hopital's rule? First, you verify that it's a L'Hopital's rule situation. So apply the limit. Plug in the 3. Get 0 over 0, right? If you get 0 over 0 or infinity over infinity, oh, there it is. In general, that means you're dealing with a L'Hopital's rule case. All right, but again, it could take other forms. All right. So this is an L'Hopital's rule, LHR. So if this were Calc 1, jeez. All right. If this were Unit 1 or pre-calc or any moment prior to that, this is what happens. So you would have to multiply by the conjugate, simplify, algebra intensive. It's the kind of thing like you know you could do it, you're just not thrilled about it, right? But you would get the job done. L'Hopital's rule tells us that if we were to take the derivative of the top and separately take the derivative of the bottom, the limit of that new ratio would be the exact same as the limit of the previous ratio. Which is really strange to think about. But what it's telling us is that the ratio of the rates of change of the two functions that make up your original limit would have the same behavior around your whatever point it is that you're concerned about. Would have the same behavior as the original functions ratio. Right? So if I take the ratio of the two original functions versus the ratio of their rates of change, the behavior is the same. All right, and it's kind of weird to think about that, but we'll explore why that is the case in the form of an activity next week. So, derivative of, again, this is not quotient rule, top separate from the bottom. What is the derivative of the square root of x plus 1? All right, the negative 2 is irrelevant. What is the derivative of x minus 3? 1. All right. So then the question would be, can I now plug in the 3 and get an answer? All right? And it's not a question you have to answer immediately. You go through the process and try it and figure it out. All right. It's going to come out one of two ways. It's either going to come out with a finite answer, a meaningful answer. It could be infinite too, it's possible, as long as it's not infinity over infinity, but it'll come up with a meaningful answer, something that's consistent with what you would expect from a limit. Or you're going to get another 0 over 0, infinity over infinity. If I plug in a 3 here and I get 0 over 0 again, then L'Hopital's rule still applies. I'd just keep going. I'd find the derivative of the top and the bottom separately, again, and then go from there. But it's not going to happen because I can't plug a 3 in on the bottom. All right. So what do I get when I plug in the 3? One-fourth? It's 1/4? No, because I heard 1/32 or something. It sounded like there was a minor debate. So is that it? Because I took a mental break here. I'm just trying. So 3 plus 1 gives you 4. So 1 over the square root of 4 gives you 1/2. Half times a half is 4. We're thinking no after school activities.
That's why I was
Because it's supposed to be over the period of 1 to 4 p.m. So that's enough for them to say we'll kill the after school activities, but they're not gonna. Yeah, this is not. I know it's not 1 p.m. So.
So you like this or less?
Yeah, this is gonna be like ongoing, off and on. This is not what the forecast is saying. The 1 to 4 p.m. is snow showers, and snow showers, even if it's in the forecast, to change.
Interesting. So it's a real possibility.
I said Joe, because 30% chance is
Why are you doing that?
I was checking the weather and look.
I just don't want to say much about dude.
They told me it's fine, but I would still be checking every hour.
Yeah, this is definitely in the territory of no after school activities.
Yeah, I really can't handle it. I was kind of big here in traffic. Yeah. I don't know what I wanted to do.
They just see
Yeah, it's a snow day calculator says 33% chance. That's 33%.
I can't tell if I have a stomach ache because I'm hungry or because I'm extremely anxious.
Probably anxious. Probably that one. I wonder.
No, this is going to smell all day.
Okay, number 2, you would have to do that using the end behavior model approach. What we're learning here actually justifies why the end behavior model approach works to begin with. If I plug infinity in for x, what do I get?
I don't remember.
Well, you'll get 5/3.
Oh, fuck.
Well, yeah.
I don't know.
That's
So we're over.
So let's keep it as simple as possible. Plug in infinity here. What do I get?
5 infinity.
Get infinity.
Oh, you got infinity.
And also,
Also infinity.
So
All right.
it's 1.
So again, this approach is going to drive the end behavior model approach. It's going to give us a justification for why we could say the limit is 5/3. But going into it, assuming that that technique didn't exist for us, we wouldn't be able to make the claim of 5/3. But because we have infinity over infinity, we're looking at something that's indeterminate. So it's another L'Hopital's rule situation.
Do we have to write when we're doing L'Hopital's rule? You just have to write like outline.
LHR is good enough for me. On the AP, of course, be more specific. But all right, the derivative of the top would be what? 10x minus 3. What about the bottom? 6x. All right, plug in infinity. On the top, what do you get? Infinity. On the bottom, infinity again. All right, so because that's the case, we know that we could apply L'Hopital's rule a second time. Take the derivative of the top. What do you get? On the bottom, you get the 6. And the limit of 10/6 is 10/6, which is the same as 5/3. If the power in your original function was bigger on the bottom than on the top, then eventually you'd get to a moment where when you plug in the infinity, you'd go to 0, justifying the case where, you know, those old rules for horizontal asymptotes, justifying the case where it goes to 0 if the power on the bottom is bigger than the power on the top. If the power on the top is larger, you get to a point where it simplifies down through derivatives, through differentiation, to give you just an x on the top, in which case it goes to infinity, or negative infinity, depending on the coefficient.
So first, I'm assuming that there's going to be situations where it's easier to do L'Hopital's. Okay.
There's that, and then there's also the cases where you're just required to do it.
Oh, okay.
Yeah.
Second chart thing up here. I haven't looked at it yet, but just like we have to memorize it and.
You should be familiar with the different indeterminate forms. When you look at the problems, the practice problems on the next page, you see that they don't all look like these 3 cases. So once you plug in your limiting constant or infinity, you'll see that it's going to take on one of those forms, justifying the use of L'Hopital's rule. Because if it doesn't take on one of those forms, then it's not a L'Hopital's rule situation, and the whole system fails.
Will the basic rule change depending on the indeterminate form?
No. All right, so this I think is the one we've all been waiting for. Because it was just, remember this rule, right? Now, if you plug in a 0, you get 0 over 0. So it's a L'Hopital's rule situation. Justifying the next step, which is to take the derivative of the top, which is cosine of x, the derivative of the bottom, which is a 1. Apply your limit again, and what do you get? 1. But you can't tell pre-calc students whenever you see the limit of sine x over x as x approaches 0, just use L'Hopital's rule to figure it out, because they don't know anything about derivatives yet. So they wouldn't know how to get from here to here. Right? So it would all just become a grand exercise in memorization. A terrible exercise. So instead of memorizing derivatives and not knowing what they mean, they just memorize the rule. Sine x over x or anything in that form gives you a 1. But then you could try this with something like sine of 2x over 2x. You could try it with 3 sine x over 2x and see how that plays out, and you can see that it ends up being a nicer approach, but of course it required you to understand the concept of a limit derivative. So that's why we had to wait, unfortunately. But it was, I think it was worth the wait, because there's a nice little payoff now, as opposed to back then we were like, oh yeah, just more math, that's cool, wonderful.
Start doing that one.
Every time we